that are associated with volcanic activity, such as the building of volcanic mountains, and also some things like climate change that are closely tied to a volcanic activity over time. So before we get into the specifics of volcanoes, I just want to introduce some more general terms that come up in this chapter, chapter 9, and one of those is geomorphology. So geo means earth, and morphology is the study of different kinds of shapes and the way things appear. And so geomorphology is the study of land surface features or landforms, and also how these things change over time. And of course, when we have volcanic activity, that's one of the kinds of processes that can lead to geomorphological change. So when we think about geomorphology, we can kind of break down the types of changes that can occur into two categories: endogenic and exogenic changes. So first of all, endogenic changes are processes that originate from within the earth, so from the ground below our feet or from layers in the earth that are below the ground. And these kinds of changes are mostly driven by plate tectonics. So as the plates move around over the asthenosphere, they grind against each other. Sometimes the plates subduct, as we discussed last time. And this kind of process can lead to the creation of volcanoes. It can also lead to earthquake activity, bending of plates, and these processes can create mountains and create geomorphological change. In addition, we have processes that we call exogenic processes, so exo being outside, and these are processes that can change landforms, but they originate from forces outside the solid Earth surface. So usually these are processes related to the atmosphere and to water that might be moving around through the atmosphere on the ground. And there's a term weathering that we use to describe the breakdown of rocks and geological material over time from wind, from water, etc. And these processes are carried out by geomorphic agents like wind, like rivers, or like frozen water, ice in the form of glaciers. It can also be a really powerful force that can scrape away, erode, and change the shape and appearance of landforms over time. So these processes, endogenic processes that are often building up landscapes, and exogenic processes that are often tearing down landscapes, are always competing with each other over time to determine the specific condition of a landform in a location at any given point in time. Okay, so now that we have that basic information, let's think about the specifics of volcanoes. And volcanoes are created as lava spews up onto the surface, and lava is liquid rock that we can see on the Earth's surface, and lava originates as magma, liquid rock that exists below the Earth's surface. So we find magma in a variety of locations around the planet, and again, it's usually associated with plate tectonic activity. We discussed two types of plate boundaries, divergent zones and subduction zones, in our last lecture. Divergent zones where plates are splitting apart, and we mentioned that that splitting allows some magma to make it up to the surface. So that's a place where we find magma and then lava existing. And we also mentioned that where plates are subducting, they can carry water down with them below the earth that allows the plate to melt, and then that melted magma can bubble up to the surface and become lava and create volcanoes near the surface. We did not at that time mention a third category, a location that's called a hot spot, so I want to bring that up briefly. And a hot spot is created on the Earth's surface when we have a plume of magma that's rising up from the Earth's mantle. So hopefully you remember from our discussion about the Earth's layers that the mantle is a layer in between the core and the Earth's crust. And these plumes are actually not very well understood. We don't know exactly why they come and why they stop occurring. But we do know is that they're fairly fixed within the mantle. And we also know that the lithospheric plates, the surface plates, move across the mantle over time, so that the influence of the hotspot is felt in different locations at the Earth's surface as plates continue to move. And at any specific given time, there's only one place on a lithospheric plate that's going to be above a specific hotspot, and that is the only location that will have the potential to form an active volcano. But there could be evidence of other locations in a lithospheric plate that have been above hotspots in the past, and so there might be kind of ancient, older volcanic material that was created by those hotspots in past times. Hawaii is a classic example of an island chain that's created by a hotspot that's sitting below the Pacific plate. So today, the big island of Hawaii, which has active volcanic activity, as we've seen over the past year, is sitting above the hotspot, and the other islands, such as Maui, Oahu, Kauai, etc., are volcanic islands, but they're volcanic islands that are extinct. There's no chance that the volcanic structures on those islands would ever erupt again because they're no longer connected to a magma chamber below the surface. So we can learn a little bit about how the Pacific plate has been moving across the hotspot, how fast it's been moving, etc. But we know that those other locations in the Hawaiian island chain are never going to be active volcanoes again. So divergent boundaries, subduction zones, and hotspots all have the potential to have lava spew out on the surface, and when that happens, we have volcanic activity. So just to give you a little bit more insight about a hotspot, sometimes hotspots occur out in the ocean, like we saw in the case of Hawaii, but we also have hotspots that can occur under pieces of continental material on plates. And in kind of Northern California and in the West, we actually have evidence of a hotspot that today sits under the area of Yellowstone National Park. And that hotspot created the magma that led to the supervolcano that occurred in Yellowstone in relatively recent geologic history, and also fuels the geothermal activity that exists in that park. But we can track evidence of past volcanic activity over the last 16 million years across Idaho and all the way into Northern California. And that shows us that the North American plate has been moving across that hotspot that lies in the mantle below our plate over the last 16 million years. So here's just some pictures of Yellowstone if you're not familiar with what it looks like. It sits at the corner of Wyoming, Montana, and Idaho. It has lots of famous geothermal features where hot water heated by magma is strewn up into the air. And then on top, we see some images of some of the past volcanic eruptions that have occurred in the area of Yellowstone. And they show the extent of the ash fall that occurred associated with those volcanoes. And you can get a sense that these were really big eruptions associated with this particular hotspot. But most of the volcanic activity around the world is not associated with these mid-plate hotspots, but instead occurs along plate boundaries. So here you can see that all these red triangles represent volcanoes, and most of these are occurring in places along plate boundaries, like the boundary of the Pacific plate that touches North America as well as different parts of Asia, etc. Okay, so when we want to think about the kinds of structures and the types of eruptions that are created when lava reaches the surface, we need to understand a property of lava that's called its viscosity. So viscosity means resistance to flow. So something that's very viscous, or something that has high viscosity, doesn't flow very well. It flows very slowly, it's very goopy, it's very sticky, and it doesn't make a lot of forward motion. On the other hand, things that have low viscosity can flow relatively well. And materials velocity or viscosity, is determined by its temperature. Hotter temperature materials tend to be more runny. You've probably experienced that in your personal life. And then also the composition, what they're made of, is also going to determine how sticky they are. So in the case of lavas, some lavas are made up of atoms and mineral structures that are more sticky, and some are made of materials that are less sticky or less viscous. However, we also kind of need to shift our perspective about viscosity when we're thinking about lava, to understand that we're thinking about the flow of rocky material. So we have all observed things in our life like oil and water that flow really well. And there's never going to be geologic material that's able to flow quite as well as that, or has as low viscosity as those kinds of liquid materials that we have interacted with. So from the perspective of a rock, if we have lava that's flowing at all, then that's pretty low viscosity compared to the usual conditions of a rock. So on the right hand side of the screen, there's a picture of a lava flow at Hawaii, and this is rock that's melted, that's flowing across the landscape, and there's two people that are standing here watching it flow towards them, and they're not doing this because they're really dumb or very high risk takers. They're doing this because they know that the rate at which this lava is flowing is not going to be super fast, so they'll probably have an opportunity to walk out of the way safely. But we still consider this kind of lava at Hawaii fairly low viscosity lava, because this rocky material has gotten hot enough that it's actually flowing across a landscape, and that's pretty significant considering that it started out as a really solid, rigid rock. On the other hand, we sometimes have volcanic eruptions that really are not associated with lava flows at all, and that's because the magma underneath the earth that comes up to the surface is so viscous, it's so sticky by the time it gets to the surface, that it really doesn't flow at all. And instead, this material creates plugs at the peak of the volcano, and then this material builds up pressure and ends up exploding into the air, into lots of solid fragments of rock and tiny pieces of ash and glass. And so the eruption that's shown in the bottom part of the slide is showing what it might look like if we had an eruption of high viscosity material, as opposed to low viscosity material on the right. So knowing that, geologists often think about three main categories of volcanic eruptions, and also three main categories of volcanoes. So it's kind of a chicken and the egg situation, where the type of eruption influences the type of volcano, and vice versa. The type of volcanic structure and whatnot has an influence on the type of eruption. So the first kind of volcano and eruptive properties that I want to talk about are associated with what we call shield volcanoes. And shield volcanoes are created when we have very low viscosity lava, so stuff that can flow. And these eruptions are not very explosive, and what happens is that lava comes up to the surface of the volcano, to the volcanic vent. It comes out, and it might be thrown into the air a bit, but it's going to land on the ground, and then it's going to flow across the landscape and freeze up into a bunch of successive layers of typically a rock that's called basalt. And these different basalt layers kind of build up over time like a little layer cake, and they create these big, large, broad, mountainous structures. So at the bottom of the slide here, we have an image of Mauna Loa volcano, which is on the Big Island of Hawaii. And this doesn't look very dramatic, but it's actually a huge mountain. It's just not very steep mountain. And this mountain is created by these successive layers of lava flows that have frozen one on top of the other on top of the other over time to build this shield volcano. So that's one kind of mountain that can be created as a result of volcanic activity. Another kind of more local example of what can happen when we have these lava flows that are created from low viscosity material spewing out on the surface is Table Mountain. So many of you guys may have visited Table Mountain. It's down in the Oroville area down near Chico, and it's this big flat basalt layer that was formed about 16 million years ago, associated with something that was called the Lovejoy Formation. And in this case, there was a volcano that's kind of in the area of modern-day Susanville that spewed this runny lava out, and it traveled significant distances across the landscape, and it pooled up in low places on the landscape, like in river channels that existed at the time. So here you can see an image of what the landscape might have looked like 16 million years ago, with hill slopes and then a riverbed. And you can imagine that this liquid lava was running down the riverbed, and then it froze up. And over the last 16 million years, these ancient hill slopes have eroded away, but the basalt in the lava flow has been more resistant, and so it has been left behind, and we can kind of see the structure of where this lava flowed in the past. So that's kind of a more local example of the result of a lava flow. Okay, the second kind of mountainous structure that can be created by volcanic activity is something that's called a cinder cone. And cinder cones are created when the lava that comes up to the surface is associated with really high amounts of gas. So there's usually always gases that are dissolved in the rock below the surface, but these are associated with pretty high concentrations of gas and pretty high pressures associated with gas as well. So as the lava makes it up to the surface, there's so much pressure from all the gas that's expanding near the surface as well that the material gets tossed up into the air by all this gaseous pressure and creates a bunch of what we call pyroclastic debris. So pyro meaning fire, clastic meaning these little pieces of rock are these kinds of small rock fragments, a little bit of glass, a little bit of ash, that's all tossed up into the air associated with this gas pressure. And as this material falls back down to the ground, it creates these very even, very steep-sided cones. Scoria is the name for some of the kinds of debris that is associated with these cinder cones. And you can see that scoria has lots of little air bubbles in it that illustrate how much gas was associated with this material as it reached the surface. And these piles of debris are very susceptible to erosion. They're not glued together very well, cemented together very well, like basalt layers are. And so as they're exposed to wind and water, they tend to erode quickly, and as a result, don't usually build up into structures that are nearly as big as the structures that we see in things like shield volcanoes. So on the right, here's a picture of a cinder cone that is visible if you visit Lassen National Park, a little bit north of us. All right, the third kind of volcano is called a stratovolcano, which is also sometimes called a composite volcano. And these volcanoes are called stratovolcanoes because they have many different kinds of layers, which geologists refer to as strata. And these volcanoes are kind of the classic volcanoes that you've seen many illustrations of and photographs of throughout your life. I have a picture of Mount Fuji in Japan here on the right, and I imagine everybody's seen images of this mountain before. And these mountains, these stratovolcanoes, are created when we have volcanoes that are associated with intermediate viscosity magma and lava. So they don't have the runniest type of material that creates shield volcanoes, nor do they have the stickiest stuff that all creates a bunch of small, loose, solid fragments. But they have different eruptions over their history that have kind of an intermediate viscosity levels, and sometimes eruptions might be associated with higher viscosity, more sticky material, and sometimes these volcanic eruptions might be associated with lower viscosity, more runny material. And over time, these different kinds of eruptions build up layers of kind of more loose, jumbled debris that's associated with higher viscosity eruptions. And then when lower viscosity eruptions occur, that material acts kind of like a gluing or cementing agent that holds everything together. And then there's a bunch of these subsequent layers that build up over time to create these really pretty large, significant volcanic mountains or structures on the landscape. And as these mountains get bigger and bigger in size, they can become quite dangerous, because sometimes when they have eruptions that are associated with this higher viscosity material, which geologists call rhyolitic magma, the rhyolitic magma can be sticky enough that it won't flow down the slopes, but instead will get up near the vent and solidify to create a big solid plug. And then as more magma builds up underneath the plug, it can create an enormous amount of pressure that at some point will create a huge explosion and eruption that sends lots of debris up into the air, and that debris can rain down on communities, and it can also set off really major avalanches, or also things that we call pyroclastic flows, which are basically really fast avalanches of really hot volcanic gases, glass, ash, and other rocks. And these events can be very dangerous for people that live in nearby areas. So these are the kinds of things that are associated with stratovolcanoes. Some examples of stratovolcanoes, in addition to Mount Fuji, that you might be familiar with include Mount St. Helens. So Mount St. Helens erupted in 1980 in southern Washington state. It had erupted previously in 1857, an eruption that was not as big as the 1980 eruption. But you can see what the mountain looked like in 1978 on the left before the eruption occurred. And then you can also see what it looked like later after the eruption occurred. And you can see how much of the mountain was actually destroyed by this eruption, and all that part of the mountain that's missing got thrown up into the air and also traveled across the landscape as very fast avalanches and pyroclastic debris that were devastating to people and ecological communities in the area surrounding the mountain. So I'll put a little clip showing this eruption on our Canvas site for you guys to view. Another example of a big eruption that it talks a little bit about in the article that you guys are going to read for your final homework assignment is Mount Pinatubo, which was or is a volcano in the Philippines, and it had previously erupted back in the 1500s, and then it erupted again in 1991, and geologists had some warnings associated with earthquakes and associated with some steam that started to come out of the top of this volcano, that this eruption was going to happen. And so there was a massive evacuation effort where they got 60,000 people out of the way in the weeks before the eruption occurred. And then when it occurred, it was very significant. So the picture on the left shows you just how big the amount of debris was compared to the mountain range that's at the bottom of the picture. So a big mountain range compared to an even bigger debris cloud. And then you can also see what it looked like after the eruption occurred. And this kind of looks like a picture of the North Pole, but in fact it's a picture of a tropical island that has been completely inundated with volcanic ash. So you can get an idea of how much material is falling out of the sky after this eruption occurred. I mentioned the final homework assignment that you guys are going to read an article to answer questions to complete. And in this article, it talks a little bit about the connections between volcanoes and climate. And one of the emphases that we have in this class is to try to think about the connections between these different Earth systems. And so I think this is a great place to illustrate a connection between a geologic system and an atmospheric system. And there's different kinds of influences that are felt in short-term ways and long-term ways as a result of volcanic eruptions. So in the short term, after a volcano erupts, there may be an introduction of many different kinds of gases from the volcano into the air. And so those gases may, one, just initiate cloud formation that can block out the sun a little bit. We mentioned that clouds have high albedo earlier on in the class. And in particular, some of these volcanic gases will create sulfate ions in the atmosphere, and these sulfate ions are really good at reflecting solar energy. And so typically what we can see after major volcanic eruptions is that there's actually a cooling in the short term, in the year or so after a major volcanic eruption has occurred. And that cooling doesn't only occur right where the volcano occurs, but in many cases occurs worldwide as these gases in the atmosphere are circulating around the planet. So I have two pictures on here that are famous paintings that you might recognize. And both of these paintings were associated with big famous volcanic eruptions. In this case, eruptions of a volcano called Krakatoa in Indonesia that occurred in the late 1800s. And these volcanic eruptions sent a lot of particulates into the air, and these particulates influenced the way that the sky looked and made lots of dramatic sunsets, in addition to causing a cooling of the planet at that time. And so both of these pictures were painted in Europe, halfway around the world from Indonesia, and you can see in these paintings that these people on the other side of the world were clearly having their atmosphere influenced by this volcanic eruption. On the other hand, while short-term influences of volcanoes are usually associated with cooling, long-term influence of volcanic eruptions often results in warming of the climate. So many of the gases that are erupted in volcanoes are GHGs, or greenhouse gases. And so if we have periods of high volcanic activity on our planet, we may have an increase in greenhouse gases like carbon dioxide, but also sulfur dioxide in our atmosphere. And as we've discussed in the past, that can cause an overall warming of the temperature of our planet as these gases trap heat. And so in particular, there's one period of time about 65 million years ago, or the time leading up to 65 million years ago, where we know there was a lot of volcanic activity. There's an area in India that's called the Deccan Traps, and there's a photograph of it on the left. You can see all these basalt layers that have built up from different lava flows that occurred during this time. And all this volcanic activity that created these lava flows spewed quite a bit of greenhouse gases into the atmosphere, which warmed the atmosphere and was one of the things that contributed to the demise of many reptiles and many of the dinosaurs towards the end of that period of geologic time. So anyway, this just again illustrates that there's a strong connection between geologic activity and atmospheric activity. All right, that's what I have to say about volcanoes. So have a nice afternoon.